Welcome back to the deep dive. So if you're an engineer, maybe a test manager, or you're running a quality team, the end of the year isn't really about winding down.
Not at all. It's all about preparation.
Exactly. It's about getting ready. And closing out 2025 means you have to be thinking about securing your data integrity for 2026. Today, we're peeling back the layers on a really fundamental process.
One that gets overlooked a lot.
It really does. We're talking about the calibration and maintenance cycle for load cells and force measurement systems.
That's right. And look, based on the materials we've gone through, we want to give you a really focused guide here. Our mission isn't, just to summarize best practices.
Right.
It's about giving you specific, actionable things you can use right now. Things that will make those planning conversations easier and, honestly, make your data unassailable.
Unassailable, I like that. So your systems are just defensible.
Absolutely defensible.
Yeah.
Especially when compliance questions come up.
And that defensibility, I think that's the real core takeaway for you today. This isn't just some chore on a maintenance list.
Yeah.
It's a non-negotiable step for quality assurance. I mean, think about it. Your load cells, these are the parts measuring thousands of pounds of critical data, safety data.
Critical stuff.
If they're not performing to spec, every single decision you make after that is just, well, it's built on a shaky foundation, so we're basically offering a shortcut to having audit-proof operations.
Okay, so let's unpack that a bit. We really have to start with why we're even talking about calibration in the first place.
Right.
There's this common misconception that, if the sensor gives you a number, it works. But that misses the entire point of what measurement accuracy is.
Yeah, it's not about just functioning, is it?
Yeah.
We know from the data that real calibration is about verifying the device's reading against a known, a controlled standard.
Exactly.
That's checking for drift. You should think of it less like plugging in a lamp to see if it works, and more like precisely setting the alignment on a high-performance car.
That's a great analogy. And the core risk here, it's like a silent killer. Accumulation
Accumulation of what?
of tiny errors. Load cells are robust, right? They don't usually have these big dramatic failures. Instead, they suffer from these small, insidious performance shifts over time.
Okay, so give me an example.
Well, say you have a 50,000-pound load cell.
Yeah.
If it drifts by just, say, 0.1%, you now have a 50-pound deviation that you're just not accounting for.
Wow. 50 pounds.
And that margin could be the difference between passing or failing a huge safety test, or worse, introducing a critical error into a new design.
So that tiny inaccuracy over time, it suddenly becomes this massive liability. So if these things are engineered to handle such extreme forces, what are the factors that actually cause these shifts?
It really comes down to the reality of material science. Mechanical fatigue is, it's inevitable.
Even if you're using it correctly.
Even below its rated capacity. Every stress cycle bends and relaxes the internal structure. Just a tiny, tiny bit. Then you add in things like accidental overloads.
Which probably happen more than people admit.
Oh, for sure. They would not break the cell, but they severely stress it. Then you have harsh environments, temperature swings, moisture, and just simple everyday wear on the connectors.
Yeah.
Basically, if a sensor is in use, its performance is shifting.
So if fatigue is this guaranteed enemy, the next question is obvious. How often do we need to fight it? What's the recommended planning cadence for these checks?
The consensus across the industry is very clear on this. Your load cells should go through professional calibration at least once every 12 months. That is the baseline.
The baseline.
For operational integrity, for audit integrity, that's your starting point.
But hold on, doesn't that 12-month rule seem a little risky? What if a cell is being used every single day in some high-cycle test? It could start drifting significantly at month 10.
That's a critical point.
Yeah.
And you're right to challenge it.
Is that rule too conservative for the really high-stakes stuff?
It is. That 12-month frequency is truly the bare minimum. The required frequency is always dictated by risk and by the application. So for those sensors in really demanding high-cycle environments, where that mechanical fatigue is just happening way faster, they absolutely need a shorter interval. Maybe every 6 months, maybe even every 3.
That makes perfect sense. It's about risk mitigation. Okay, so let's dive into what makes a calibration service, world-class versus just standard. When you're trying to justify the cost of a premium service, you need to know what you're actually paying for.
It all starts with traceability and having low uncertainty. The calibrations have to be NIST traceable.
NIST, right. For anyone who doesn't deal with the paperwork, that's the National Institute of Standards and Technology.
Exactly. And that traceability means the whole measurement chain links back to national and international standards. It's absolutely vital for compliance, for that defensibility we talked about.
And that's just the foundation. The tools they use for the calibration must be just as important as how often they do it.
Well, absolutely. And what's fascinating here is the kind of hierarchy of measurement. A high-quality calibration uses reference materials like NMI certified gold and Platinum standard reference load cells.
NMI, so that's National Metrology Institute.
Correct. And that certification means those reference cells have the absolute lowest possible measurement uncertainty. You're basically checking your working sensors against the most accurate force measurement devices on the planet.
Wow.
And this is often managed by proprietary software, like the gold standard software mentioned in the sources, which can handle all these complex environmental compensation algorithms that your standard tools just can't touch.
So that level of detail using NMI certified standards is what really elevates a standard check into a superior maintenance cycle. And we should be clear about the scope. We're talking about load cells, but this applies to other things too, right?
It does. This level of service applies to torque transducers or even complete integrated measurement systems. The goal is to ensure the entire unit goes back into service, performing exactly as it did on day one.
Right, better.
Or better, yeah. That's the goal of preventative maintenance. But, sometimes prevention isn't enough. We need to talk about what happens when things start to fail.
So transitioning from prevention to repair, what are the obvious signs that a load cell needs more than just a quick check, that you might need to pull it from service immediately?
Right. And based on the research, you need to be actively watching your data logs and the physical sensor for 3 major red flags.
Okay, what's number 1?
The first is just obvious data instability. You'll see erratic readings that fluctuate wildly or for no reason at all.
And the second?
The second is more subtle. It's signal drift. This is when your 0 point, your baseline reading, starts to shift consistently over time. That points to structural instability or an electronics issue.
And the third is just looking at it, I assume?
Pretty much. Physical signs, obvious damage to the cables, the connectors, the housing itself. These things can compromise the shielding or introduce noise into the signal. If you spot any of those 3, your system is compromised.
And once you spot one of those flags, what should you expect from the repair cycle? It's not just like soldering a broken wire, is it?
Oh, absolutely not. The repair cycle has to be rigorous because it's all about getting back to that state of data integrity. It starts with a really detailed evaluation, both physical and electrical, to find the exact cause of the failure.
And then after the fix?
After the repair, it goes through a complete performance verification. The goal is to bring that sensor back to, or even better than, its original factory specs.
Yeah.
And the documentation of this whole process is just as important as the repair itself.
That brings us perfectly to the planning cycle that you are probably tackling right now. You're closing out 2025, you're preparing for 2026 budgets and schedules. This is that strategic window.
Precisely. And the argument for scheduling your calibrations and potential repairs now is overwhelming. It goes way beyond just saving money.
Although that's a big part of it.
It's a huge part. Preventative maintenance is always more cost-effective than an emergency repair. I mean, downtime in the middle of a test is incredibly expensive.
But strategically, scheduling now gives you control. You can minimize that extended downtime, which is why the good services offer quick turnaround options. Getting those assets out the door and back on the floor fast is crucial.
And this is where your asset management really ties into compliance. A high-quality provider doesn't just hand you a certificate. They maintain a detailed, ongoing history of everything.
So service dates, performance data,
calibration certificates, all of it.
And that detailed history, it's not just for passing next year's audit, is it?
No, it serves a much bigger purpose. That history should be a core part of your asset lifecycle planning.
How so?
By tracking how quickly a specific sensor degrades, how fast it drifts, you gain predictive capability. You can start to forecast when a sensor needs to be retired.
So you can justify capital expenditure requests for 2026 with hard data.
Exactly. And it simplifies your whole annual review. It ensures your investment is protected and that your planning is proactive, not reactive.
That's the ultimate payoff right there. You're moving from just documenting failure to strategically managing performance risk. By planning now, you guarantee compliant, accurate, and truly defensible data for all of next year.
So what does this all mean for your next team meeting? Well, ensure calibration is on the schedule for at least every 12 months. Make it a priority to monitor for signal drift and those erratic readings. And use this window right now to schedule those services.
To minimize cost and maximize efficiency. An excellent synthesis. But let's leave you with one final thought to mull over, building on that idea of more frequent calibration for high-stress assets.
Okay.
If we know that mechanical fatigue and simple wear are guaranteed to cause these performance shifts, and if that standard 12-month cycle might be too long for your most demanding applications,
then the critical question you should be asking for your own efficiency is this. What continuous data-driven monitoring strategies could you implement? Instead of waiting for that arbitrary 12-month mark, how can you leverage your historical performance data?
and maybe run more frequent spot checks.
Exactly. To predict when a sensor is about to fall outside its acceptable tolerance. How can you safeguard your most critical tests with a truly optimal, personalized calibration frequency?
That's the level of efficiency to strive for. Get those service plans locked in now, start 2026 with confidence, and we'll catch you on the next deep dive.